Welcome to 6.7 Constructing a Two-Proportion Z-Interval. Today we are going to follow a similar method to what we did with one proportion. However, this time we are going to be working with two different samples. First thing, I do want to remind you we will be following the steps of panic. We're going to define the parameter, but this time it's going to be for both groups. Check assumptions and conditions, again for both groups. We'll name the inference method, calculate the interval, write our conclusion in context. All of these steps are almost identical to what we did with one proportion, just slightly different because, again, we're dealing with two samples. First thing, defining the parameter. So remember, we are calculating a confidence interval to give an interval of plausible values for an unknown population parameter. With two proportions, generally we're looking at the difference between two samples. So we need to define both of them. First, I have P1, which is going to be the true proportion for group 1. P2, which is going to be the true proportion for group 2. Remember, you're going to want to add some context in there in order to receive credit on the AP exam. Another thing, if you happen to label P1 and P2 differently than I do not worry. On AP grading and on my grading for tests, I have both ways written. I have both calculations that could be possible. There is no right and absolute way to order these two different parameters. Checking assumptions and conditions. They are the same assumptions and conditions. We're going to first check if it's a random sample. Both of them should be coming from one random sample, or both samples should be selected randomly. Kind of depends on the language of the question, but you just want to make sure that you have that randomization condition built in. Another possibility is if you have an experiment, if you've randomly assigned treatments, that also satisfies the randomization condition. 10% condition, the sample size n must be no larger than 10% of the population. We are familiar with this. We're going to do it for both groups, N1 and N2. Success failure condition, we just want to make sure that we have at least 10 successes and at least 10 failures. Again, we are doing this for both groups, and we are using our sample statistic p hat in order to calculate this, just because we don't know what the true proportion is yet. Now, naming the inference method, this is where things get a little bit different. We are going to call this a two-proportion Z-interval. One important thing that you have to include is how you are setting up your problem. Are you doing P1 minus P2? Are you doing P2 minus P1? There's no right way to do it, but make sure that you define it so that they kind of can follow along with your work and match up your correct answer to the correct answer that they have on the grading rubric. Now, when actually calculating a confidence interval, we're taking a point estimate plus or minus a margin of error. The margin of error breaks down into the critical value and the standard error of statistic. This is the this is the same formula as standard deviation. The only reason why we call it error is because it is calculated using hats and not the true proportion. So not quite the standard deviation, but as close as you can possibly get. And one thing that is also different is we are taking the difference, and that's why it's important when you're naming your test to state how you are subtracting. P1 minus P2, P1 hat minus P2 hat, plus minus our critical value. These are going to be the same as they were for one proportion. Remember, if you can just remember what they are for the most common ones, you don't have to go in and calculate. 95% confident has a z-star of 1.96. 90% confident has a z-star of 1.6449, and 99% confident has a z-star of 2.5758. These are the three most common ones, but if you do run into something that is not one of these common ones, just remember your confidence interval is in the middle. So say, for instance, it was 98. I have 98 in the middle. That would give me 1 in this tail, 1 in this tail. I just take inverse norm of, if I'm reading left to right, it would be 0.99 instead, just if something like that comes across. But for now, these are the three most common ones. I wouldn't necessarily worry about anything else. Last thing you have to do is go ahead and write your conclusion in context. So we can be however many % confident that the interval from blank to blank captures the true difference. Key word here, make sure you're talking about the difference in the proportions of whatever the context of the question is. So last thing before we actually get into problems, I will be showing you how to do them by hand, but I'm going to follow up with how to verify in the calculator. Calculator steps for the TI-84. You're going to go to Stat, Tests, 2prop zint, which is B. This is going to be right underneath the calculator function we use for a 1prop, which is A. It's going to ask you for X1, N1, X2, N2, where X is the number of successes, N is the sample size, and it will ask what confidence level you want. One thing to remember with the calculator, if you enter in a decimal number for X, if you enter in something like 2.7 or 2.8, it's going to give you an error. That number has to be a whole number in order for your calculator to correctly calculate the confidence interval. So let's get started. Example 1. A survey was conducted to compare the proportion of adults and teens who use social networking sites daily. The first survey took an SRS of 950 U.S. teenagers ages 13 to 19. The second survey took an SRS of 2,975 U.S. adults. In the two studies, 83% of teens and 72% of adults used social media daily. Construct and interpret a 95% confidence interval for the difference between the proportion of teens and adults who use social media daily. So the first thing I'm going to do is kind of go in and highlight some important information. First thing, I'm constructing a confidence interval. Know that, always a good place to start. The next thing, I took an SRS of 950 teens, and I got that 83% of them use social media daily. And I have another sample. I have a second SRS of adults, and 72% of them used social media daily. So I know that I have two samples. I know I'm constructing a confidence interval, so we can go ahead and get started with our steps of panic. The first thing I want to do is define my parameter. So I'm going to define P1 as the true proportion of US teens who use social media daily. I will describe P2 as true proportion of US adults who use social media daily. Once I'm done defining my parameter, I'm going to check my assumptions and conditions. The first one is are my samples random? Well, I have an SRS and I have an SRS. So what I can say is both samples are stated as SRS. The next thing I want to do is my 10% condition. And if I take both of my sample sizes, I can assume that there are at least 9,500 teens and 29,750 adults in the US. Seems reasonable. The third condition is success fail. So I'm going to work with teens first. N is equal to 950. P1 hat is 83%. So I'm going to multiply these two things together, and that's going to give me 788.5, which is greater than 10. Same thing, 1 minus 0.83 is 0.17. So when I multiply these two together, the number of fails I could foresee is 161.5, which is greater than 10 as well. I do the same thing for my adults, where my sample was 2,975, and my P2 hat was 0.72, gives me 2,142 and 2,975, which are both, 833, which are both greater than 10. And when both conditions are met, when I have all four inequalities deemed to be true, we can say that our distribution is approximately normal. All conditions are satisfied, so I'm going to full steam ahead on our interval, but let's name it first. I'm doing a 2 proportion z interval for P1 minus P2. And again, you can do P2 minus P1. You're going to receive a similar interval, you just will have the opposite sign. But they will match your answer to how you describe the calculated difference. So make sure you don't halfway through switch it up on them. So I'm going to go through these steps using my calculator after I calculate it by hand. So I have the formula P1 hat minus P2 hat plus or minus Z star all times the square root of, well, my standard error. You can see it. So I'm going to go ahead and fill in what I know. I know that P1 hat is 0.83. I know that P2 hat is 0.72. I know that the Z star for a 95% confidence interval is 1.96. And filling in similar information for P1 hat in 1, P2 hat in 2. And one thing that I want to remind you is when you are looking at something like this, a confidence interval formula, sometimes it's nice to go ahead and calculate this second half of the formula just so that you're able to identify margin of error. Not necessary all of the time, but if you do have a question where they ask you for margin of error in one of the steps, my advisement is always to read through the entire FRQ first. This is where you would find it. So once I calculated all of this, I got a confidence interval of 0.0812 to 0.1388. Now that I have this, we are going to go ahead and look at it in our calculator. So let me go ahead and open that up. So I have my calculator. I'm going to go to Stat, going to go over to Tests, and then I'm going to go up technically to B, press Enter. So my first number of successes, and remember we have to be careful because we are going to be using our calculator. So I'm going to round 788.5 up to 789. And then my sample size was 950. And I have 2,142 out of 2,975, confidence level of 0.95. And I'm going to calculate, and I'm going to get something very similar to what I have from my method using the formula, 0.0817, 0.1393. And again, it's slightly off only because we had to round that number of successes up just for the calculator to give us an output. This is not something that they would necessarily take off for on the AP exam because they do know that the possibility of you using your calculator is there. So I went ahead and wrote my conclusion with my confidence interval that was calculated by hand. We can be 95% confident that the interval from 0.0812 to 0.1388 captures the true difference in the proportion of teens and adults who use social media daily. And remember, do not forget to write a conclusion anytime you are doing an inference test. Okay, example 2. In October 2000, the U.S. Department of Commerce reported the results of a large-scale survey on high school graduation. Researchers contacted a random sample of 25,138 Americans aged 24 years to see if they had finished high school. 84.9% of the 12,460 males and 88.1% of the 12,678 females indicated that they had high school diplomas. Create a 95% confidence interval for the difference in graduation rates between males and females. So again, I am going to start by identifying that I am creating a confidence interval. I'm going to look at my possible samples. I have 84.9% of 12,460 males, and I have 88.1% of 12,678 females. So 2 samples, creating a confidence interval. We are going to first define our parameters. I have P1 is the true proportion of U.S. males age 24 who finished high school. P2 is the true proportion of U.S. females age 24 who finished high school. My first condition is randomness, and they told me initially that my random sample of 25,138 Americans. So even though they just took one sample entirely, they took that entire sample using a randomization method. So we're going to say that this satisfies that condition. And you can kind of repeat what they say. I just said the 25,138 Americans were contacted randomly. The next thing, we can assume that there are at least 124,600 males and 126,780 females aged 24 in the US. Again, makes sense. Success fail condition, I have first dealing with males sample size of 12,460. P1 hat is 84.9. That gave me 10,578-ish, which is greater than 10, and 1,881-ish, which is greater than 10. Similar for females, both of my values are greater than 10, so I can assume that this is an approximately normal distribution. Now I'm going to name my method, 2 proportion Z interval for P1 minus P2. Again, you could do P2 minus P1. A lot of the times I have students who prefer to keep that difference as a positive value because they do not like working with negatives. So technically the females have the greater P hat and they like to write that first, which is okay. I just went with P1 minus P2. So I plugged in what I knew into my formula. 0.849 minus 0.881 plus or minus. I'm doing a 95% confidence interval again. So that's a Z star of 1.96. And I have my standard error calculated with P1 hat in 1, P2 hat in 2. This gives me a confidence interval of negative 0.0404 to negative 0.0236. So I am again going to show you how to do this in your calculator. I'm going to pull that up if it wants to open. There we go. So stat over to tests, and I'm going to go back up to B. This time I have to enter in my X1 and my X2. So let me see if I can drag this over so I don't have to keep going back and forth. So X1, I'm going to round this up to be 10,579 out of 12,460. And for X2, I'm going to round. I always suggest if you're dealing with samples, you always want to round up one. So I'm going to do 11,170. And my sample size was 12,678. Confidence level of 95. Calculate. And I get negative 0.0405 to negative 0.0236. Very similar to the confidence interval I have. I'm very accepting of that wiggle room just because I do have a rounded number of successes. Going to write my conclusion. We can be 95% confident that the interval from negative 0.404 to negative 0.0236 captures the true difference in the proportion of U.S. males and females aged 24 who have graduated from high school. Now, the next question asks, does this provide strong evidence that girls are more likely than boys to complete high school? Well, with my idea of doing P1 minus P2, technically I'm doing males minus females. So when I get a confidence interval that is entirely negative, so I have negative percentages, that means that the female proportion must be higher. So in some statistic language, Our confidence interval is telling us that the proportion of U.S. females, context, age 24, who graduated high school, is between 2.36% and 4.04% higher. Higher is important than the proportion of U.S. males, age 24, who graduated high school. There is going to be strong evidence that women are more likely than men to complete high school.